Good morning. My name is Paul Stoddart. I'm a member of the Air Power Group Committee of the Royal Aeronautical Society, and I'm here to welcome you to today's Royal Aeronautical Society webinar and to introduce the speaker and his subject. The webinar today will be recorded, and as part of the domestic issues I need to go through to begin with, the YouTube video link will be shared with all attendees 2 days after the webinar through an email that can be accessed, shared free of charge. There'll be a Q&A session following the presentation, so please submit your question via the questions function on your control panel during the presentation, and we will cover as many of these as we can. Please keep your questions short and specific to the webinar subject. All attendees are in listen-only mode, so if you wish to communicate with us, please do so via the questions function on your control panel, and one of the organisers will respond. The event itself, the presentation will be followed by some Q&A period, and we'll aim to finish at about 12 o'clock. The presentation itself will last between 35 to 40 minutes. I'll now introduce the speaker, Dr. Michael Pryce. He is the Senior Analyst, Future Projects Research. Mike owns Future Projects Research and is currently contracted to the Defence Science and Technology Laboratory on a number of projects. Until 2019, he was a lecturer in defence acquisition at Cranfield University, where he ran the Low Cost by Design Research Network and acted as an independent scientific and technical advisor to the Ministry of Defence. Previously, Mike worked at Manchester University, carrying out research into improving combat aircraft support costs, which was funded by the Pentagon. He also worked on a systems engineering project looking at the Harrier and Typhoon programs with BAE Systems, and in the BP-funded International Centre for Advanced Materials, exploring global business opportunities for new technologies. Mike's academic background is in technology policy and the history of technology, with a focus on the 6-decade saga of jump jet development leading to the F-35B. Prior to becoming an academic, he worked as a process engineer for General Motors and in web applications development for Sun Microsystems. The title of the presentation is The Supply of Future Combat Aircraft. Mike will explore the challenges in meeting the future needs for combat aircraft across the globe. It will look at enduring issues that challenge the development and support of future combat aircraft and how to overcome them within resource constraints and political limitations. And 3 main areas will be explored: design for combat air, a low-cost industry, and combat air transformation. These will build on work he's done as an advisor during the development of the UK Combat Air Strategy. The webinar will take into account recent developments in the United States, Europe, and East Asia, where public debates are rapidly evolving, and the presentation will explore their applications for the UK. I'll now hand over to Mike for the presentation itself.
Okay, thank you, Paul. Hopefully by magic I've appeared. Thank you for that introduction, and good morning, everybody, or good evening, or very early morning for some people, I understand, who are listening around the world. I'd like to thank Society for asking me to give this talk. I should point out I'm not an air power person. I'm looking very much at the supply of the material means of achieving the ends of air power. The title I've chosen is quite an old-fashioned sounding one. There was a white paper the British government came up with in the 1950s that talked about the supply of military aircraft. But I do think in many ways a lot of the issues we're now facing echo some of the problems that were faced back in the 1950s and in the 1980s. They seem to be perennial issues, and that's really my focus, is what are the constant problems that we face? How can we perhaps overcome them by learning lessons from the past, and perhaps sometimes applying the lessons we thought we learned in the past but misapplied last time round. So what I will be looking at, and if people are interested, I'm on Twitter if people want to engage afterwards. I know there might be time for all the questions. But as Paul said, I will be looking at the design for combat air. That's a UK term for fighter airplanes in lots of ways. But the question really is, how can we create new fighters? This is something that's a lot of countries around the world are facing at the moment, is how do we actually come up with what are in many cases manned fighters, but also unmanned ones in some cases, or unpiloted or remotely piloted. There's various unsatisfactory terms for combat aircraft that have pilots in and don't in many ways. But is it the case that we actually have an industry and a capacity that can deliver new fighter airplanes? If it is possible, can we make them affordable? It's well known that they're getting ever more expensive. Going back to the 1950s, combat aircraft costs were not a big issue for a lot of people. Into the 1960s, they became so, as they became ever more expensive. And currently, it's one of the real fundamental problems we face. So how can we actually reshape what we do in industrial terms so that we can supply combat air power in an affordable manner? And in order to do that, what sorts of transformations, what sorts of fundamental changes do we have to make? Is it the case that we just take the existing industry with its historic legacy of doing things a certain way, apply that to the future and try and do it for less money? Or do we have to really fundamentally alter what we're doing in order to change in such a way that we deliver long-term sustainable air combat capability in an affordable manner? And just to give an idea of how the past sometimes can shock and surprise, the picture in the background there is a design for a hypersonic fighter aircraft that the UK tested in model form in the 1960s. The idea being that that would fly up to about Mach 5 at very high altitude and then launch something into space that could deal with satellites and shoot them down, or space capsules and all sorts of things. It would give the UK a space combat capability. And such things have been looked at frequently in the past. And often people have walked away from them for good reason. And I would say one of the things to remember is always what didn't we do, and why didn't we do those things? And are we trying to do them now? And if so, are we able to actually achieve things that people in the past couldn't? So it's really looking at those enduring issues and perhaps understanding the problems that are so hard to overcome that if we're going to be affordable, we may be sensible not to try to overcome them at all, but to walk away from them. So looking at where we are at and where I am talking from, if I have one single message, it may be a controversial one, it's that currently no one can really design combat aircraft in a way that meets all of their needs. So it may be that we can produce a sophisticated system, and by we I mean any particular country, but can we produce it in the numbers that are required? Can we produce it in the ways that enable us to update it over time, to adapt it to changing circumstances, or in some cases to say, well, let's throw that one away and start again? Because often, because of the sheer cost of the things, it's very hard to justify spending a lot of money on something and then only using it for a short period of time. But perhaps that is what we need to look at, not as much as we've been spending on programs, but spending a little bit less, using them for less time, and actually getting back to a situation where what I see as being synthetic design is possible. I would say that we've arrived at a situation now where we've got analytic design. We spend a lot of time doing studies. In the UK, we have for 32 years now, since 1988, been looking at various programs that would come after the Typhoon, the European fighter program. That's a third of a century of studies. That's an awful lot of time of analysing and trying to understand what is possible. And other countries have done the same. In the United States, we've had the F-35 program, but even the F-35, when you look into the origins of it, there are things that look very much like the fundamental concept of the current F-35 being drawn in the mid-1980s. So it's arguable that in terms of conceptual studies, we've done lots of them, but not generated anything new in that time. And I would say a lot of that's to do with when you're, people talk about analysis paralysis, but it's really difficult if you're in a resource-constrained environment. You're trying to understand all the problems that you may face, to get trapped in that kind of loop of, well, we could do this, but. And what we really need are people who are able to synthesize new designs quite quickly and to form a logic about that design that perhaps isn't necessarily supported by data, because we haven't done anything like this before and we don't have data, therefore you can't analyze it, but do understand what they're doing and are willing to actually make the case for what they're trying to do. Those of you who are aware of some of my work know I spend a lot of time looking at jump jets, too much time perhaps. There is Margaret Thatcher in 1982 touring a jump jet design team, who were coming up with a very odd looking device which had a twin boom fuselage and so on. And when you look at it, and when she looked at it, she certainly had some questions. She engaged with the design team in unexpected ways, clearly being quite briefed in terms of what they were doing with that design. But what they could do is say, yes, it does look peculiar, but it looks peculiar for certain reasons. We don't necessarily have all the numbers to say, yes, it will definitely work, but we are convinced that we think it will. People are still discussing, I've seen online forums in the last few days, people are still discussing this design and whether it would work. And one of the problems is people do not want to go ahead with the program until they feel, yes, we know it's going to work, because these things are so expensive, because we're stuck with them for decades. We want to have this analytic process that convinces us it's going to work before we move. And I would argue that actually that inability to move is the fundamental problem we face. And it's been caused by what I term here as the destruction of creation. There's lots of talk in innovation circles about the necessity to have creative destruction. But in reality, what we have lost, I think, in many ways, is the ability to sensibly create new things that probably will work. And that is often what was done in the past. Lots of, again, looking at the jump jets, you look at the Harrier, in theory, it's impossible to fully explain how it stays up in the air. We know the mechanisms by which it does, but how they combine was very hard to understand. But clearly it worked. So how do we get back to a situation where we can actually get on and develop things quite quickly, rather than waiting to be convinced that we know it's going to work in advance of actually trying to do it? I would say that is the fundamental problem. Now, there's lots of ways to answer how you can do this. It's very well for me to preach, well, we just become synthetic designers, and how do you get on and do that? It is a case, I think, it's dependent absolutely on certain types of people who've had certain types of experiences. And it is the case, unfortunately, that the industry has got smaller over the years. Programs have taken longer, so people with the experience of new programs have become fewer. How do we get them back? Well, happily, I would say we don't need vast numbers of them. But equally, it's not a case of you just take 10,000 STEM graduates and sort of fire them at the latest program you've got and hope a few of them are the ones who have this ability to synthesize design. They also need to have things to work on. And one of the ways I'd say that you're able to have things to work on is to have something that you're willing to allow fail, but actually may learn something from it. And in the past, essentially what happened was competition provided that mechanism. You'd have design competitions, you'd have fly-off competitions, you'd have programs where you'd have short production runs for one aircraft and longer production ones for ones that became successful. So there's lots of talk at the moment of, in the States, of what they're calling the digital century series, and seeing the century series programs as ones to emulate. But actually the ultimate century series fighter was the F-110, which was the Phantom, really the F-4 Phantom. For a short period of time, the US Air Force labeled it as the F-110. And what you can see there is actually that competitive environment. The one that wasn't developed as part of the Century Series program, was outrageously developed by the Naval Service, actually was the one that came through, partly for political reasons, partly because that winnowing process that competition allowed people to see both it was good in predicted qualities, but also in the actual reality of what was delivered. Some of the other Century Series aircraft had certain problems. One of the most famous, one of the first ones, couldn't even fly supersonically, even though it's intended to. So there was lots of technical issues that they were facing at the time. And the way to overcome them essentially was to have several bites of the cherry to see which would actually produce something that was useful. And that ability to build and test is certainly something that globally has been lost since the 1980s, in the UK since the 1960s in lots of ways. And we have, as I said, moved into this situation where it has to be right first time. We have to nail this. So we spend forever trying to figure out, how can we nail this? How can we prove on paper and on computer screens that what we're doing is going to work? And oddly, air is a very strange substance. It's very difficult, even looking outside of kind of the digital systems that people concentrate on, just to get an airplane to perform the way you want. Predicting how an airplane will work is something that cannot be done necessarily on the desktop. Often you do need to actually fly them to find out what happens when you're at Mach 1.4 and go into a very tight turn, just how much speed really will bleed off versus what the computer says. So computational methods allow you to do the basics, but they don't actually allow you to know what's going to happen. And we are, as I said, caught in a loop trying to achieve something that's unachievable in theoretical terms. We have to get back to a situation where we build and test things. Now, one of the issues people say that is so important that it's limiting what we're doing is, okay, we want to build and test things, but they're innately expensive things. So having built something, we're almost committed to it anyway. It's very hard to say we've just spent 2, 3, 4 billion pounds on something and we're going to throw it away. The last picture shown is the F-22, which obviously was part of a fly-off competition in the United States in the 1980s. And if you look at lots of the concepts around the world at the moment, they often look somewhat like the F-22. They're stealthy, twin-engined, air dominance type fighters. It looks like the wheel is often being reinvented in lots of ways. And to me, it's interesting that there are lots of people who say that the F-22 shouldn't have been produced. It should have been the YF-23 that Northrop produced. I'm not going to get into such a debate, but what was interesting was there was a variety of designs, a variety of approaches, and that the US Air Force was in the happy position where they could fly them, try them, and choose the one that they thought would work. Equally, they could see that actually sometimes some of the requirements we've laid down, when we've actually got our hands on them or seen how hard it is to produce an air vehicle that meets those requirements, it's not so attractive. And that idea of informing a requirement, I think, is an important one. But a fundamental issue is the ATF, Advanced Tactical Fighter Fly-Off, did cost quite a few £billion. It's arguable whether it subsequently saved billions of pounds because the program shifted to the right, was extended in time frame, the total numbers reduced, and ultimately the main threat disappeared. So there wasn't the incentive, I think, to press that program as hard as perhaps it could have done. The initial plans, if I remember rightly, were to have it in service in the mid to late 1990s. And in reality, the ultimate development batch aircraft were only flying at that time. But this idea that we need to slow things down to save money, I would say, is open to question. Equally, the fact that is there enough money? Well, yes, there is. If you look at how much air forces globally spend on actually all the material things they need to do to deliver and develop capability, we see the majority of costs often are not in design and development and production. They're in sustaining the abilities. Across the life cycle, you can often see 60, 70, 80% of costs for an entire program are in the support phase, operations and support. And what you can see within the operations and support phase is that if you break down the costs, around 70% of that 70% or so is itself maintenance activities. It's spanner turning activities to keep the aircraft flying. Around 30% is often spent on updating the aircraft. But that 70% of 70% is still around half of the total cost that you spend on these aircraft are on maintainability and reliability. If you can reduce the need for those, you can release large amounts of money for development. So I think if we look at where the money is spent on combat air in the round, we can see that actually there is scope to change how we do things, perhaps release some money to do things differently. That's not as easy as I'm making it sound, because you have to balance your program and your portfolio of platforms across their different life cycles and across the period you want to sustain a capability. But I do think it's really important to understand that development may look big, support is bigger, but by reconfiguring how we do support and taking some of that money, we can actually reduce what we spend on turning spanners essentially and turn it into capability. That may also sit with how the future workforce lies. Maintenance activities are perhaps not as attractive to STEM graduates as design and development activities. You may find it's easier to recruit. And certainly one of the big changes in the structure in the UK industry was a recognition in the mid-80s that actually demographics meant there'd be a smaller pool of people to get maintenance crews from. During the mid-80s, the RAF did a study and they found that directly around half of their costs were in maintenance. And if you include some of the overheads, up to 60% of their total costs were in maintenance-based activities, or they had these overheads to support maintenance. So the sums potentially are very, very large. Trying to release that and turn it into capability, I think, is the financial trick that can be done. Equally, post-Cold War, we had a situation where the idea that there was all this money in maintenance activities meant that businesses naturally moved into that area. Because programs had been shifted off to the right, we were using older platforms longer. So there was this vicious circle of more and more money being spent on maintenance activities for platforms that weren't really necessarily what you wanted. And at the same time, studies were being done saying we've got no money to move ahead with this. I think having a better discussion in terms of how we can release money from support into design is really fundamental to developing new capability. In order to make that money something that works for an industry that currently is, in some cases, very heavily dependent on support and upgrade contracts rather than initial development, I do think we need to move more towards a focus on production. Production traditionally is where industry made its money. You don't sell aerodynamics, you don't sell, you develop software, but what you sell are complete aircraft, the structures, the systems that go within them. And that is traditionally the business model that was had. It's been disrupted in lots of ways by default rather than by design in the subsequent 30 years since the 1980s. But getting back to a situation where actually you have more aircraft, that because you're making more of them become cheaper potentially. I do think there's a big issue where a lot of the supposed costs that we see, Augustine's infamous law, where costs apparently just rise and rise for new types of aircraft, can equally be interpreted as actually, as you produce fewer of an aircraft, they become more expensive. Simple economic laws operate. So I think there's an issue where if we can release money, get into a development cycle that allows us to get something into production relatively quickly, then that generates profits for industry, which they can reinvest in new developments. And equally, could be the case that rather than have to upgrade the actual physical same airplane over 40 years, you can every 10 years or so throw away the old airframe, perhaps take some systems out, put it into a new airframe that has slightly better performance and so on. And actually you upgrade on the production line rather than on the maintenance line. That could be a more attractive option for industry, allows gradual evolution and allows this approach to synthesis that I talk about, where you have people within industry trying to learn how to design airplanes. It gives them that experience of doing it. This, though, does engender potentially rapid change. And we have had a situation where we can see now that perhaps the introduction into service of a new aircraft can take as long as the entire life cycle of platforms did in the past. Looking at the current F-35 and going back to Typhoon, F-22, things that have come into service over the last 3 decades or so, you can see that actually the step from first delivery to initial operating capability can be many years, and from initial operating capability to supposed full operation capability can be almost forever. It never quite arrives. It's a constant process of updating what are, by the time they get updated, old, worn out physical aircraft. They need rewiring and so on. And that's again where you get into this vicious circle of the maintenance costs increase, but the actual development capability is diminished in lots of ways. I do think also that production is the area where it's easier for organizations to be seen in collaboration programs that organizations have developed around production. Typhoon, Tornado in the past. The example there of the Harrier, first produced in the UK and then co-produced with the US, and then subsequently Italy and Spain joined the program almost at the end of its life as part of the production activities. So production does allow people to buy into programs over time in unexpected and unusual ways. You don't necessarily have to plan it all in advance. Often with joint programs, what you find is that it's in the maintenance phase that joint production falls apart, and you find different organizations want to maintain them differently because they're facing different threats, they're facing different budgetary conditions, and you find that you have fleets of different types of tornadoes and typhoons. It's very, very hard then to get benefits from scale in maintenance activities. Moving back more towards a production focus for industry, I think could actually see benefits of scale. And like I said, can release funds if you do it in a smart way that allows you basically to remove some of those maintenance costs that have built up over time. So how have we arrived at where we have, and how can we make this glorious future actually into a reality? Picture there of a chap, General Bernard Schriever, famous rocket man from the 1950s, created arguably systems engineering and project management as a byproduct of his attempts first to transform how combat aircraft are developed, and subsequently to create space rockets and nuclear missiles. Lots of technologies that we're now familiar with came out of these enterprises, but equally ways of managing and ways of understanding technical issues equally were created by Schriever. And I would argue that actually what we've done is we've taken a kind of a rocket science model of technology and applied it to combat aircraft, when in reality it's much, much harder to develop a combat aircraft than it is to develop a rocket. Rockets are typically single use up to now. We've now got rockets that can come back and land thanks to Elon Musk. But even with not having single use, they are single role. Their mission is usually quite well defined. They transit the atmosphere in very predictable ways. They haven't got to suddenly start pulling G, pumping out chaff and jam things and try to react to a very radical tactical situation that was unexpected. So this idea that combat aircraft actually should use the systems engineering approaches that were created by Shriver, the project management approaches that were created to enable these sorts of activities, is, I think, open to question. And potentially by changing how we run programs, we can actually realize the benefits that I've highlighted in the earlier part of this presentation. For Shriver, he was quite a pushy chap, progressed quite rapidly through the US Air Force, and he was very much a proponent of we must apply science in order to meet our ends. But what he actually did was he transformed combat air in his time in the early 1950s in response to the Korean War, and then moved on to rockets. And actually the outcome was the Century series that earlier I mentioned wasn't the great success that people thought. Applying Shriver's weapon system concepts in the Century series programs actually led to very, very narrow platforms like the F-102, the F-106 that had a narrow mission set, were not necessarily terribly flexible, but were quite expensive. And as mentioned, what actually won through was the thing that was developed outside the US Air Force, not applying rigidly the weapon system concept in its early stages, the F-4 Phantom, which was designed as a kind of a general purpose airplane. It was ground attack as a concept, and then it was air combat as a concept, and then it ended up doing all those roles and missions ultimately, because it wasn't tightly bound to a particular mission when it was designed. But equally, it wasn't decided that because it's not the maximum performer in one particular area, we should disregard it. So I do think there are lessons that we can learn from the now apparently distant past, because our actions are in many ways still controlled by that distant past. Our understanding of technology is formed on a systems basis. And another one of the things that may be controversial, I would say every time you hear people talk about systems, you should probably double the cost of that expected thing that they're talking about. And if they start talking about systems of systems, you should probably square the cost. Because what you're talking about when you talk about systems is building in increasing complexity. And in the Cold War environment, that made sense. The idea was we will outdo the enemy by actually producing systems that perform one time only, but perform very well. And in the 1950s, the assumptions around nuclear war did mean that one time only really did mean one time only. There wouldn't be a second attempt. But I don't think that's the situation we're necessarily facing today. So why do we manage as if it's going to be one big show rather than ongoing series of unexpected events that we need to respond to? Hence the fact that designing combat aircraft isn't about rocket science. It is about this idea of design as synthesis. It's about people who can understand that the future is difficult, you can't predict it, but you need to design something that is innately sound and flexible, the absolute essence of air power, and can be readily adapted to unexpected futures. And that is not something that can be done at the computer screen or at the drawing board by anybody. So we have, I think, over a number of decades got into a kind of a systems trap where we think that what we are doing actually can meet the future, but in reality, it cannot. And when we look at lots of the programs and platforms we currently have, you think about Typhoon, it was designed very tightly around a specific single mission, which was to fire a missile at supersonic speed and pull a sharp turn to get away from counterfire from the enemy. I'm not aware of it ever having done that. I would be surprised if it ever actually did have to do that. But what we're stuck with are update costs as a part of the aerodynamic and integrated systems designed to meet that mission. That mean that just putting a new type of bomb or a new targeting pod on a Typhoon takes much longer than it could possibly, because you have to update the entire system. The unstable aerodynamics are a real fundamental problem, as are the integrated avionics. Similar issues faced by the F-22, where when you read the original history of the F-22, what you see is it was going to do everything quite cheaply, and they're going to use modular avionics that would have a few different types of electronic cards within each computer box, and that would reduce maintenance costs. It actually became quite the opposite. It became a maintenance nightmare in lots of ways, because the only users of those cards were the US F-22, maintenance crews. So they didn't get the economies of scale that they hoped for. And arguable as well, I think that stealth in and of itself may be valuable for some missions, but like the Typhoon's tight turn at supersonic speed, is that an overhead you necessarily want to carry around all the time? And there's lots of things you can see. There's a web article I saw recently about some cracked structure on an F-22, and you can see that the surface materials that have to be applied in stealth platforms bring quite a substantial manufacturing and maintenance burden with them. And could it be possible perhaps to have certain aircraft that are of a common design, but some have the coatings applied and some don't, and therefore don't need them maintained, for example, and therefore you can reduce costs? Is it the case that you could have, when I read the history of the F-16, they were quite worried that actually it wouldn't, the fly-by-wire system wouldn't work, therefore it couldn't be unstable. So they actually designed the structural frames in the fuselage so you could move the wing back and bolt them on a different position to make the aircraft stable if that turned out not to be the case. And actually it's arguable that in that case, then you can have a cheaper system if you've got a fly-by-wire system where you don't have safety critical issues when you update the aircraft, because it's not so unstable, so the nose isn't going to suddenly depart. So there's a whole host of technical issues you can look into and futures you can prepare for in relatively simple ways by adding bits of structure or leaving out certain components that may allow you to have a cheaper, more flexible future. But I do think we need to think about these problems more openly and more widely than the narrow Cold War 1950s nuclear war view that actually structures programs and management thinking about these programs and has done for many years. The weapon system concept is fine if you're going to fight a nuclear war. If that's not what we're planning, why are we using concepts from the Cold War to understand how we actually deliver on technology? So this glorious transformation, this glorious dream, how can we realize it? And I think it is about both looking at the technology and how we manage it, and understanding better that actually perhaps sometimes doing things that actually deliver on the original intent of prior programs without getting caught up in the problems they subsequently got themselves tangled in could be beneficial. So as I've mentioned, looking at the ATF, the original intention, it was going to be relatively cheap compared to how it turned out to be, partly because they bought 180 or so rather than 750, it cost more, partly because it took longer to save money, it cost more. But equally, the technology changed. It became the case that actually avionics progressed so that modular avionics, commercial approaches to software development were available off the shelf rather than needing to be developed in-house. And by moving quite slowly, but locking in that technology at an early stage, what became the F-22 program couldn't perhaps benefit as much as it might have done. Equally, the European fighter program, originally the future European fighter aircraft, or as the Americans refer to it as 5 Europeans, because the French were involved, 5 Europeans fooling around, that's the polite version of what they used to say, was seen by many as a reinvention of the Hornet. So the key differentiator became that, well, the Hornet can't pull 3 or 4G at Mach 1.4 trying to get away from an opposing missile shot from the enemy, but this aircraft could. But as I've said, that overhead of that single mission, EFA was developed as a weapon system, all the documentation in the archives now, so it's sufficiently old. Actually, the National Archive of Kew has quite a lot of material about the European fighter, talks about it as a weapon system, and it's that weapon system approach that locks in a lot of those costs, didn't allow the flexibility. Once you entered into a very tightly bound collaborative approach where different partners want a share of each and every box, almost every computer card is kind of parceled out among the organizations involved across nations, what you found is very, very hard to change. And equally, what became the F-35, people have their views on how much it cost, but certainly the dream originally was that it should be the cheap partner to go alongside the F-22. Why hasn't that worked? And it's arguable because actually we've got locked into this very big, complex system, both in terms of the technologies involved and the way we structure them organizationally across nations, that's led to this failure of saving the money that was expected. So is it the case that we have to revisit how we assumed we were going to do these programs in the past, then understand why they went off in perhaps the wrong direction, and change what it was that changed that direction? And I would say it's actually the misapplication of management and organizational approaches that has meant that originally good ideas were not enabled to flower. So I don't think it's necessarily a technological issue. It may well be an organizational issue. And that organizational issue equally is one that across nations they have problems with. But equally, you could see kind of an almost idealized approach where instead of having different countries competing and saying, this is our concept, and you can either join it or stay away, perhaps actually they could collaborate and cooperate and compete jointly on several platforms and programs and have a winner-takes-all approach. In the 1950s and 1960s, NATO sponsored many joint combat aircraft programs. There's a lecture online for the Society that I delivered about 8 or 9 years ago now on the Hawker P1154, which is a supersonic jump jet. One of the interesting things I was found about that program was not the technology that was used, it was the approach that actually nations in different countries came up with their own designs, entered what was the largest international design competition up to that point, but actually sat down and agreed, well, if your design wins, we will co-produce it with you. But for the moment, we're going to compete our design. So there are some lessons from the Cold War that actually perhaps we could apply. Rather than trying to go for work share, perhaps we go for what's the best thing that we all need, structure IP in such a way that it means no one organization, no one nation controls everybody else, but equally people buy into those things. And you do see steps towards that. This talk was prompted in part by some of the advice I gave a couple of years ago in the combat air strategy was being developed. And within that, I saw that there's a range of possibilities of how you could do things in the future that weren't necessarily being explored when everybody's default was to look at the last couple of programs and think, well, how can we just do them a bit better rather than understand what did we do wrong in those programs? How could we correct it? Perhaps there are wider benefits that can be realized. It is the case that combat air is still seen as immensely expensive. There's a report I saw yesterday that the Japanese program is talking about 90 aircraft in total for an acquisition cost of $47 billion. That's a lot of money. It's $500 million per aircraft. Is that the world we really want to move into? How would you husband your resources in terms of looking after and protecting those aircraft rather than putting them at risk, which ultimately is what air power is about. It's about putting your material goods at risk in an environment where potentially something bad might happen to them. Equally, if you've only got 90 aircraft and if half of them are in a hangar and half of them are parked outside and there's a sudden hailstorm, you've got very few assets that actually you might be able to use subsequent to events. And we've seen it, in Japan, they've had various natural disasters that actually have led to problems where they have lost significant numbers of aircraft from what are a small fleet. So there are all sorts of issues that need to be looked at, but the broad issue is we essentially need to produce more aircraft, we need to produce them more cheaply, and we need to get away from this environment where essentially once we've produced a very few very expensive aircraft, we feel we're stuck with them and have to kind of fiddle and fix them for 40 years in order to have viable air power. Because I think what that's led to is a situation where we're on the verge of not having any viable air power at all, while other countries perhaps who are spending slightly differently may outpace some countries that, in the West, the traditional West, and cause problems. And I think we're at a point where we have to talk about, is this a new Cold War we're entering, and therefore we have to have Cold War approaches, or is it not the Cold War? We shouldn't look for analogies from the Cold War. We should try to do things differently, do things better, and deliver the air power for the future that's really needed, as opposed to replicating the mistakes of the past, which have led to the problems we've got in the present. So at that point, I will stop talking. Hopefully you've been able to hear me. No one has been, I can't see what you're seeing. I can only see my slides in front of me. I'm happy to open the floor to questions, which I understand Paul will be able to pass over to me.
Mike, thank you very much for what was a very stimulating and thought-provoking presentation. We do have a number of questions, and I will try to get through as many as I can. I can't guarantee getting through all of them, but I would still urge people who have yet to submit a question to do so, and I'll certainly pick what I think are the best of the bunch. Starting off then, Mike, you mentioned the success of the F4 Phantom relative to the Century series fighters. I think you mentioned the F-102, the F-106 and so forth.
Yeah.
What other examples are there of a successful general purpose aircraft such as the Phantom?
At risk of outraging some people, the F-16, I would say, is an example of that, even though it was actually designed very narrowly. It was designed to win in John Boyd's beloved kind of air combat, where you just get behind someone and shoot them down, hose the so-and-sos, as he used to say. But in reality, as I mentioned, it was the actual designers worked in such a flexible way that it has turned out to be quite adaptable. The actual engineering design work that was done was quite smart. The approach to keeping costs down was, if we want range, we reduce drag rather than increase fuel. It was those sorts of approaches. So it's what do we take out rather than what do we put in. And I think that's an example that you can look at globally has been very successful. From other countries, you can see the MiG-21, the most produced jet combat aircraft. I think is still the case. In many ways, mirrored the F-16. And there are certain common themes you can see in some of these, which is they have a modest load of avionics. They have the most powerful engine you can get your hands on and stuff it into the smallest airframe. Part of the process of creating a small airframe is there isn't much space to jam more avionics in, and therefore you may save cost. Now, people have different views and different experiences about this. I've talked to various people who've flown F-16s over the years, and as often the case, the last airplane, or the airplane that people spend most time flying, is often the best one. That's their view. The ways I've met people who've flown the F-16, their experience was very striking, even if it doesn't necessarily mean it's the one that they want to replicate in the future. And they can see that for what it does it quite well. It doesn't necessarily mean that their particular nation is looking for that in the future. But I do think the F-16, a lot of the talk is about the concept work that was done, John Boyd and the fighter mafia and all that. But in reality, if you look at what Harry Hilliker did within General Dynamics, it was the actual design of the bits of metal and so on, their understanding of the fundamentals of aircraft design that is more interesting and has resulted, I think, in a more successful aircraft. And that was a similar case with the F-4 as well.
The questioner had an addendum to that question. Are there any examples you can offer of a successful general purpose aircraft, combat aircraft from the UK aircraft industry?
Hawker Hunter. When we say from the UK industry, actually half of them were paid for by the Americans. They were built, I went through the records of the factory a few years ago. Actually, all the tooling came from Italy, and the machine tools, that were the cutting tools and so on, came from America. The jigs came from Italy, and a lot of the aircraft went abroad. It was a very multinational program right from the outset, and was designed to have flexible production and to be adaptable. The structure of the aircraft could be broken down into main modules. They had single seat Hunters where they'd take the nose section off and put a two-seat section on, and you'd have a trainer. It was literally a very flexible aircraft. And I believe until about 2 or 3 years ago, there were still more Hawker Hunters on the UK military register than F-35s. They're not flown by the RAF, but they have military serials because they're flown by aggressor groups that deliver services to the armed forces. But in terms of something that did quite well, that's an example from the UK where I think something like that was achieved. I'm trying to avoid saying the Harrier because people will know that's often my stock answer for lots of things. But the Harrier itself was quite adaptable, but in a different way from the Hunter. You had to have very different versions of the Harrier over many decades.
Okay, thank you. Changing tack somewhat. The next question is, while we may not be intending to end up in a Cold War or a total war scenario, if we do not maintain high-end capability against certain nations, I'm sure they'll come to mind, are we handing those potential adversary nations the ability to act with impunity?
Potentially. I mean, interesting statement there is that if we maintain high-end capability, and often maintenance is the problem. It's all well and good if it performs on, in trials very well, but if it's parked in a hangar when the fight kicks off, how useful is that? If you only have a few of them that can't be in the fight because they're located in the wrong place, how useful is that? And again, there is this issue of quality versus quantity. But I think you see that through a lens of maintenance. What is the highest end capability that you can actually reliably produce on the day? And that, I think, is a bigger question that hasn't really been asked. Equally, our view of what high-end capability is often, I think, leads to that situation we're currently in, where you see lots of kind of F-22 clones being created. you do have to wonder what the market would look like for combat aircraft if the US had exported the F-22. Would people who bought it and experienced it have thought we need to now produce another version of that? Or would they have thought, actually, that's not what we're really after, because we can only afford a couple of dozen of them at most. Even the Americans couldn't afford as many as they would like by a long shot. So there is an issue of what constitutes high-end capability. Is it what the best thing you can get in good numbers for an unpredictable fight in the future versus the thing that fits with your simulated combat of the future if it performs as advertised rather than as experienced?
Okay, thank you. There have been several questions concerning the engines, which obviously form the core of any combat aircraft. As you mentioned, the F-16 philosophy of design was to put the most powerful engine in the smallest possible airframe. I'll try and combine the various engine questions so that we can cover that topic in one go. The first one concerns parallel development of a new airframe with a new engine, and the example that the questioner offered was that of the Bristol Olympus in TSR2, and what was implied as a higher risk by having two levels of new technology running in parallel. And another is the potential of variable cycle engines for future combat aircraft.
Okay. I would say I've just lost a bet, because I was told TSR2 comes up in every presentation. I said, no, I don't think it will in this one, but it has done. With that example, the idea was that the Olympus wasn't a new engine, although it was so modified that it became a new engine. That program had other issues. I talked to the chief project engineer from Wharton, chap Ivan Yates, who ran BAE systems effectively in the 1980s. He, despite having spent a big chunk of his life on TSR2, his view was it was a terrible program, the worst collaboration we ever had, even though it was a UK-only program. It was because it was two design teams that worked together quite poorly, and that then resulted in design decisions that were made, for example, putting the wheels in a position that made the fuselage structure very, very narrow, which meant actually getting the engines in and out was hugely problematic. It would probably have induced huge maintenance problems. I understand they had to produce basically tailor each engine for each tunnel. So there were issues all throughout that program where taking an engine, developing it to its ultimate limits, and then putting it in an environment that didn't really suit it because it was running very hot, caused all sorts of potential problems. And I think it was probably good that it was cancelled. But equally, I think a bigger issue with jet engines, when you look at the history of them, is when they were introduced, they actually massively reduced maintenance costs. Old fighters, the big powerful piston fighters at the end of the war, the Typhoons and Tempests of yore, their engines shook their airframes apart. When Meteors came into service, what you saw is a halving of the total maintenance load on a typical fighter squadron because of the lack of vibration. So there's a big issue here that jet engines show, which is actually you can introduce a new technology if it reduces the maintenance burden that you have. But with something like a variable cycle engine, does that have broad benefits both in the mission and in the cost approach that you're trying to live within, or is it the case that that technology is a huge development burden with uncertain outcomes? Those are the sorts of questions I think you need to ask, as opposed to can you make it work? Looking at the F-22, they looked at the variable cycle engine there, and the US Air Force decided to walk away from it and say that the risk versus the potential benefit isn't there. It may be the potential benefits are still there, but how do we realize them? And engines are not particularly my thing. I heard them described once as basically all they do is they slap the air and set it on fire, which is a gross simplification of what goes on inside an engine. But yeah, obviously, if you're going to have a new aircraft that you want to perform at certain speeds and so on, and certain efficiencies, you need to develop a new engine. That then often becomes the big determinant of your cost. If there isn't a concomitant benefit from using that engine, it could be actually that you're ending up in a kind of a TSR2 type situation where it becomes the fundamental problem that causes lots of knock-on problems and kills the program. But with anything, it's trade-offs. Sensible, smart people making good trade-offs rather than people saying, here is the latest best engine, here's the latest best form of nose wheel, here's the latest best form of radar. If you stick them all together, we'll get the latest best fighter airplane. What you'll probably get is a load of unexpected problems.
It's only a point to ponder. You mentioned your concern about anything described as a system, where you said that you should immediately double the cost estimate, and if the phrase system of systems is used, you recommended squaring the original figure. A question has been presented. Tempest, the Tempest program, described as a system of systems. Is that a big mistake?
I don't want to. Well, we all use the common language. Everybody, the word system, if you ask people to define what they mean by system, different people come up with different meanings. Even I spent a lot of time talking to aircraft designers of the past, and I once had a round table at BA Wharton many years ago. And what was clear was that for some people, what they meant by systems was a series of pipes that were connected, a hydraulic system, and for others, what they meant by system was everything you could possibly do with an airplane. And the original concept of a weapons system, for example, when the chap I showed, Bernard Schriever, he saw it as it's not just the aircraft, it's the training, it's the doctrine, it's everything involved in delivering a capability, as we now see it. It's a very modern concept. And over time, it kind of became, well, it's the airplane and the stuff that's in it, or it became the radar and how that functions. What people see as a system becomes is quite hard to define. But I do think that trying to understand that sometimes a federation of systems doesn't necessarily mean you've got a system of systems. It's when people try to make everything across all the different objects to work together as closely as possible, you have problems. I do know that what's been talked about in public is sometimes you have a very simple approach for different entities to talk to each other. And in that case, you can say, well, is it really a system? Is it just two things that have a very simple method of communication rather than are tightly integrated in all sorts of different ways? So it's a very odd word that's used very, very freely. But what I would say is when people are making an issue of it and making it out as if this is a good thing, what to me I think systems then mean suddenly is complication. What they're doing is they're adding complication and complexity into something where perhaps they should be looking for something simpler. And that's why when I say people are making the case for systems, it becomes problematic. But obviously, there are systems in the world. The plumbing in your house is a system. It doesn't necessarily mean that your house is absolutely dependent on its plumbing, just as an aircraft isn't absolutely dependent on its hydraulic system, unless you start getting into complex fly-by-wire systems that actually make great demands on the hydraulic system. So you have to understand what the pilot will be doing to design the hydraulics in more detail. So it's a problem word. I think we need better language for what we're trying to do. We need to understand clearly what is meant by systems. But proponents of systems, I think, are often baking in additional cost.
Okay. I have to say at this point that there are quite a number of questions that have come in, and they are on a range of subjects, and pretty testing questions as well. And I apologise to those who have submitted them, for whom I won't be able to raise their question.
I'll go for shorter answer.
There won't be enough time. It wasn't an implied criticism of you, Mike. But
I'm
trying to arrange across the variety of subjects that have been raised, and moving on to a new topic for the next question. It says, you have identified rightly that support costs are an increasing proportion of through-life costs. How much of this might be driven by an increased regulatory burden? And then an associated question, how do we reduce support costs?
Regulation is part of it. I don't think it's the greater part. Traditionally, if you go back to World War I, the great majority of the RAF were maintenance crews. Relatively simple aircraft with piston engines had huge problems, as I said, because of vibration and things like that. And what you saw was just rigging a biplane actually took a lot of effort, a lot more than the kind of delivery at the front line that the pilots and the aircrew would do. It's a perennial issue with aircraft that maintenance is a huge burden, especially aircraft that you're using in unexpected ways, which is what combat aircraft do. So I think you kind of have to accept that there is going to be relatively large amounts of maintenance. But the way you deal with that issue is by doing smart things in design and development. You can reduce that burden. So just looking at, I'll talk about the Harrier because I've avoided it mostly so far, but in a negative sense, in lots of ways, it wasn't designed for frontline service. It was designed for it sort of experimentally. What they rapidly found was once they started using even the prototypes, the back end used to shake and vibrate an awful lot. and that caused all sorts of failures. And the avionics in Harry were certified to their own special standards. They couldn't use the generalized standards, and that drove in an overhead burden. So what the design team learned from that is, for the thing we have to design in the future, that thing that I showed Margaret Thatcher looking at, we have to get rid of that problem. So what they decided to do was, rather than to design better ways of mounting avionics or better cooling systems, it was literally, let's just move it out of the way. Let's put the avionics on booms under the wings, and the exhaust therefore don't wash over them. Now, lots of people had lots of problems with that, but you could see the underlying logic they had, which was, yes, it will actually cost 20% more to build the airplane, but it will probably halve your maintenance costs. And that seemed like a sensible trade to them. And I think that's the way you deal with maintenance, is through smart design. You have to really understand what causes maintenance. With avionics systems, you have what's called 70% no fault found failure rates, where actually it seems there's nothing wrong. It's arguable if you don't have the avionics in there in the first place, then you won't have the no fault found burden that drives a lot of maintenance costs. So there are various ways to get rid of it. It's by understanding the problem better.
Okay. Changing the subject again, the issue of weapons has been brought up. And the question is, do you have a view on where weapons feature in a future vision? Often there is a substantial cost associated with that integration. And I think the extension of that question might be, how might integration of weapons and perhaps other systems be achieved at a lower cost than those currently normally experienced?
I'm probably just a one-trick pony, so I'll kind of echo the same answer I said, which is through smart design. If you understand the example I mentioned of Typhoon, because it had unstable aerodynamics, highly integrated avionics, they drive a lot of problems in updating it, because you have to recertify the system, you have to perform all sorts of potential activities. I was involved early in my academic career with moving between Typhoon and Harrier, and what was very interesting was that Harrier was a simpler platform in lots of ways, less sophisticated, but actually was much faster to update. You can hang a new targeting pod on it much more quickly and get that into the front line. So there's a case there to be made for, actually, if you design in simplicity, you are also designing in speed of adaptation. And is that what you really want? Or do you want a sophisticated platform at the outset? Or do you want one that's not terribly sophisticated, but is more quickly adaptable? And I think the same goes for weapons. When you're hanging a new weapon on, how much integration activity do you get involved in? Is it the case that all the intelligence is in the weapon, you just kind of point and shoot? Or is it the case that you're getting data from the aircraft into the weapon and you have to make sure that all that works well, to know that when you press the button, it's going off and doing a job that's politically and legally compliant, and ethical issues are addressed. There's a whole lot of issues that come in to complex systems that weren't there when they were originally designed. And I'm a great believer in simple, open architectures, therefore allow you to adapt quickly. Like I said, there are, people are working on this stuff currently around the world. People understand the benefits, they have done in the past. It's just delivering on it becomes problematic because of the way we do things.
We're coming up to the hour, and I think there's probably only going to be time for one further question, but I will try and amalgamate a couple of themes that have come out. You've talked about the approaches of analysis and synthesis and their differing benefits and drawbacks. The question is, what are the main lessons that should have been learned, and why have they not been learned?
It's a very big question to finish. I'll try. I would say that actually simplicity brings benefits, and these are, keep it simple, stupid, and all those sorts of things. The skunk works in the States made this case. It's arguable the skunk works as it was doesn't exist anymore, but that approach is still one that's very attractive. You look at things like the SR-71, the F-117, they were relatively simple in lots of ways, very designed around certain specific missions. So that may not be the answer you're looking for, but that approach of actually having a focus on, when you make design compromises, you make them in the direction of simplicity rather than complexity, is easy to preach, but very hard, I think, to deliver in the lived front line of engineers. And I heard a talk from the Society a couple of weeks ago, an update on Team Tempest, where there was a description of how in the F-35 program, engineers would turn the computer on in the morning, it would tell them what to do. And is it the case that you've got the system telling you what to do, that actually you'd have to fight against that to get your ideas of simplicity in, if the system is already about a complex system? So there's issues here where I think at the outset you have to be very firm, very clear, very strong in your in being a proponent for simplicity and fighting against the drift towards complexity, which is hard. It's like an ocean current. It's hard to see except by where you end up. And I think that is what we need to fight against.
Okay, maybe time for just one final question, looking through the various topics and examples given. In terms of the option of iterative development, where an airframe has a relatively short life and the upgrades are on the production line rather than during the actual service life of a particular airframe. If we take the Tornado as a potential example of that approach, what upgrades would you have predicted perhaps for the Tornado GR1, GR4, and maybe GRX, if it had had a longer life in terms of production, shorter life of an airframe, and a series of upgrades on the production line? What might we have seen?
I would say it would have been very hard to do with Tornado, both because of the physical object was quite complex, very dense aircraft with lots of stuff in it, and also the program with multiple partners causes all sorts of problems. There's the old guy saying, if you want to go there, I wouldn't start from here. I think that would be the issue with Tornado. I would say if you
want to choose another example aircraft, that's fine.
Yeah, F-16, I'd say that you could see that even the designers, one of my, with my airplane nerd head on, one of my favorite old designs is the F-16 XL, which is what Harry Hilliker ended up with when he looked at actually how the Air Force were using it. So it wasn't John Boyd's dream of turning and burning, it was actually a bomb truck, and what you saw was you do need more fuel. You also need not to have an increase in drag with that fuel, and we get the drag reduction by putting the bombs on in a smart way. And you can see that the potentials in the F-16 program versus what was realised, for whatever reason, illustrate some of those approaches that could have happened. So the F-16 did have those alternatives created; they just weren't put into service. I'm probably getting a lot of outraged views from people in America on this, but I'm happy to continue such discussions on Twitter.
Okay, well, Mike, thank you very much. With that, I'll bring the Q&A session to a close. If you could put on the final slide, please. Thank you. As I mentioned at the beginning, the video recording of today's webinar will be emailed out in about 2 days' time, and it's free to access and free to share. And everyone will also receive a survey so that they can feedback how they feel, how the webinar went. And we clearly welcome any constructive criticism as to how to improve in the future. We hope you found today's event interesting and useful, and we look forward to seeing you, at least metaphorically, at future webinars. So I'll just conclude by thanking Mike again for an extremely interesting presentation, and to all the attendees, I hope you enjoy the rest of the day and these current times. Hope you stay safe and well.
Thank you, Paul. Thank you, everybody. Goodbye.